This is our video about types of intermolecular forces that we sometimes call IMFs. And we're also going to talk about the strengths of those IMFs. Now, just to review, when we talk about what are intermolecular forces, they are attractive forces between molecules, or it could be attractive forces between molecules and ions if ions are present. Now, the reason why molecules would be attracted to each other revolves mostly around how the positive end of one molecule will be attracted to the negative end of another molecule. If we look at an example like CH3Cl, and I draw two of these molecules, and I look at the Lewis dot structure, I can see that one side does not have electrons. We call that the electron poor side, and because it doesn't have many electrons, it has a partial positive charge. The side with a lot of electrons carries the partial negative charge. So if I do that for each of my molecules, the attraction that we're looking at is the attraction here, the attraction between the partial negative on one molecule and the partial positive on the other molecule. And that's how polar molecules are attracted to each other. The positive end of one polar molecule is attracted to the negative end of another polar molecule. But this can also happen with nonpolar molecules. With nonpolar molecules, they can have what we call a temporary dipole, and while it has that temporary dipole, they can be attracted to each other. And we're going to talk about how that happens. And just a reminder, these intermolecular forces, these attractive forces, are relatively small compared to bonding forces. So they are not as strong as a bond. The reason why that's true is because the charges are generally smaller. It's a partial positive and a partial negative, not like ions that have a positive and negative charge. And the attraction is generally over much larger distances. So even though they are attracted to each other because they're farther apart from each other, they don't feel the attraction as much. So for both of these reasons, intermolecular forces are not as strong as bonds. These are the types of intermolecular forces that we will be covering. And we're not going to do them exactly in order. We're going to talk about dipole-dipole first, then we're going to talk about dispersion, then we'll talk about hydrogen bonding, and then we'll talk about ion dipole. Now, I really like this chart because not only does it tell us the names of the intermolecular forces, but it also talks about what types of particles can have those intermolecular forces, and we're going to explain those as we go through each one. And then probably the most important part of this chart is the strength. What this chart is telling us is that dispersion forces are the weakest and ion dipole are the strongest. And that's something that we have to keep in mind because we're going to talk about how intermolecular forces affect physical properties and why ion dipole is so important and dispersion makes less of an effect. So we're going to start by talking about dipole-dipole intermolecular forces and how polar molecules can have this kind of force. When we talk about polar molecules, we say that they have a permanent dipole. They are always polar. Another way of saying that is that they have a dipole moment. So when we look at the name dipole-dipole attractions, it's really because polar molecules have a dipole moment. And so when we think about this name, it's really saying polar molecule attraction. So don't let that dipole-dipole name catch you up. It's really just a polar molecule attracted to another polar molecule. Now, because these molecules have a permanent dipole, they are always polar, they have attractions between the molecules. The positive side is attracted to the negative side of another molecule. And what's really important about that is those attractions raise the boiling and melting points of polar molecules. So polar molecules have higher boiling and melting points than nonpolar molecules. So let's look at a picture of dipole-dipole forces. What we have here is a carbon chain. It's actually C3H6O, and this is another C3H6O. And when we look at the Lewis dot structure, it actually looks like this for each one of these molecules. And if you make the VSEPR structure around this central atom, it's trigonal planar, so it looks really much more like this. And that's what we're seeing here. The reason why we have this partial negative charge and partial positive charge is that when we look at our Lewis dot structure, the lone pairs around the oxygen make that the electron-rich side, and this side that just has the hydrogens with no lone pair is the partial positive side, the electron-poor side. So when we look at two of these molecules and how they would be attracted to each other, the positive side of one here is attracted to the negative side of the other, just like opposites attract. Now again, because both of these molecules have what we call a permanent dipole, they are always polar. This attraction is constantly happening when these molecules are in a beaker with each other. So now I'd like to look at some data, and I know that there are a lot of numbers on this chart. I'd like to focus in on one line at a time. I'd like to compare nitrogen gas to carbon monoxide. Now I've drawn the Lewis dot structures for each of these molecules. Nitrogen gas has a Lewis structure like that, and carbon monoxide looks like that. And they actually have quite a bit in common. They are both two-atom molecules. They both have a triple bond. They both have relatively the same molar masses. And they both have lone pairs of electrons on the outside. So they have a lot in common. But let's look at the difference in their properties. The boiling point of nitrogen is at negative 196. The boiling point of carbon monoxide is 192. So the boiling point of carbon monoxide is actually higher, and the boiling point of nitrogen is lower. Now what those boiling points mean are that nitrogen gas is easier to boil. Another way of saying that is it's easier to take from a liquid to a gas, so it's easier to separate the molecules from each other. Carbon monoxide is harder to boil, and it's harder to take it from a liquid to a gas. It's possible, but it just takes more energy. And the reason why that's true is because nitrogen gas is non-polar. There aren't these dipole-dipole intermolecular forces between the particles. On the other hand, carbon monoxide is a polar molecule. There's more electrons on this side because of the difference in electronegativities. And so this is the negative side and this is the positive side. It's a polar molecule, and so it has dipole-dipole forces. It has strong intermolecular forces, and so that holds the carbon monoxide molecules together, and they do not want to go from a liquid to a gas. All right, so that's how we explain dipole-dipole forces. Dipole-dipole forces are attractive forces between the negative side of one molecule and the positive side of another molecule, and any polar molecule can have these dipole-dipole forces. Or I should say every polar molecule has dipole-dipole intermolecular forces. And now I'd like to start talking about dispersion forces, which are another type of intermolecular forces. But unlike dipole-dipole, where only polar molecules can do it, dispersion forces can be exhibited by all molecules and atoms. Right. So here we have a picture of just a diatomic gas molecule. And on average, the electron distribution in a nonpolar molecule is symmetrical. That means that there's the same number of electrons on this side as there are on this side. This could be something like a chlorine gas molecule. Something like this, where there's the same number of electrons on this side as on this side, and there's no difference in electronegativity, so there's not any polarity in this molecule. So in nonpolar molecules, the electron distribution is symmetrical, and that's what we're seeing here. But one thing that we have to remind ourselves about that might be kind of hard to imagine is that when we talk about electrons, so if there are electrons in here, they are moving totally randomly, and it's not like they're paying attention to each other than to try and get away from each other as much as possible, but they are moving totally randomly. And what happens is that once in a while, more electrons happen to be on one side of the molecule than the other. And this is what happens. What happened here is that kind of for an instant, more electrons were on this side of the molecule. And in that instance, there's more electron distribution on this side, and it becomes a partial negative charge, and that takes away electrons from this side, and so it gets a partial positive charge. So what we're saying is that in any instance, there might be an unsymmetrical electron distribution, and that gives the molecule a temporary polarity. So dispersion forces are just temporary dipoles. It's like the molecule appears to be polar for a short amount of time. And during that time, when it has temporary polarity, it has attractive forces between the positive side of one molecule and the negative side of another molecule. Because this doesn't last very long, it's a much weaker force than when the molecules have a permanent dipole. Now we just said the dispersion forces were much weaker than dipole-dipole forces, so that's up on the weak part. This is stronger. And the difference is they're both polar attractions, but this is temporary and this is constant. Now going back to our molecules with a temporary dipole, the attraction has to do with how many electrons you can get on one side of the molecule versus the other. So if you can create a situation, or the molecule itself creates a situation, in which there are a lot of electrons on one side, so there's a lot over this side, and very few on the positive side. The bigger the difference between the positives and the negatives, the more attracted these molecules are going to be to each other. Now, the word that describes how much of a mismatch there is, how many more electrons there are on one side versus the other, is called polarizability. How polarizable is the molecule? Can you really get a lot of electrons on one side and not many on the other? If you can, it's a very polarizable molecule. And that polarizability is what influences the strengths of the dispersion forces. So any molecule can have dispersion forces, but some molecules will have stronger dispersion forces than others, and it depends on a couple things. The first one is the volume of the electron cloud. If there are more atoms, that means more electrons in your molecule and a larger electron cloud. That means that you can get more of a mismatch, and that means stronger attractions. The other thing that influences the strength of a dispersion force is the shape of the molecule. If there's more surface-to-surface contact between the molecules, the attractions are going to be stronger. Now these are both things that we're going to talk about in some later slides when we can show some data. Now before we go on, I want to talk about how a molecule with a temporary dipole will influence the molecules around it. And for a second, I don't want us to think about this other molecule. We're going to pretend that it's not there for right now. So say we have our molecule, this guy here, and its electrons have just, for whatever reason, kind of instantaneously, there are more on this side than there are on that side because the electrons are moving totally randomly. That just happens once in a while. And when that happens, we get a partial negative charge on one side and a partial positive charge on the other side. Now if we look at how that influences other molecules around it, anything with a partial positive charge is going to pull electrons towards itself. So if there's another molecule like this somewhere near our molecule, its electrons are going to get pulled towards the partial positive on our first molecule. Now when that happens, when the electrons in this molecule are pulled towards that side, it gives this molecule over here a temporary dipole itself. It gives it a more negative side, and the other side is more positive. And we call that an induced dipole. Its dipole, its polarity, was induced by being near another molecule that was polar. And this is why polar molecules can create dipoles in molecules that don't normally have dipoles, but are polarizable. So as long as a molecule has electrons and is polarizable, it can be influenced by the polar molecules around it. And we just call that an induced dipole. And all molecules are susceptible to this. Now, even though all molecules can do this, or all molecules can have an induced dipole, the ones that are polarizable, or the most polarizable, will have the strongest induced dipole. When we talk about polarizability, remember, it's a measure of how we can get a charge distribution to be distorted, so more of a mismatch. So the more mismatch we can create in a molecule, the more polarizable it is. I've heard people kind of describe polarizability as a measure of a molecule's squishiness, how much its electron cloud can be manipulated. Now, when we talk about the strength of induced dipoles and how they affect the world around us, it actually explains some things that you might be aware of. You might just not have thought about the reasons why. And I want to use the example of how oxygen gas and even things like iodine will dissolve in water even though it doesn't seem like there should be much attraction between those two particles. Let's start by looking at the Lewis dot structures of oxygen gas and iodine. Both of these molecules are nonpolar, and so they don't really have a positive and negative side to them at all. But water is a very polar molecule. It has those two lone pairs of electrons on one side, and so this is the very negative side, this is the very positive side. And what happens when these interact with each other, so this is our water, and this is our oxygen gas here. What happens when these things get together is that the electron clouds on the water push away the electrons on the O2. So these electrons repel these electrons, and it pushes it further into the molecule. And what's happening there is that the dipole of water, the fact that water is a polar molecule, induces a dipole on the oxygen gas by distorting the electron cloud. Now I know that the picture over here got cut off, but what it had was that the water molecule over here pushed away the electron cloud, and it made the electron cloud much bigger on the far side. And that induces a dipole, which means now this is the slightly more positive side, and this is the slightly more negative side. And the way that I'm drawing my electron cloud over here, I'm just saying that there are more electrons on this side of the molecule than there are on this side of the molecule. And now because there are those partial charges, the water molecule and the oxygen gas can be attracted to each other. So you might be thinking about why we're spending so much time talking about oxygen gas and water and why they would be attracted to each other, why oxygen gas will dissolve in water. And it really comes down to something that's really important for biology. Fish need dissolved oxygen to be able to breathe underwater. And if oxygen will not mix with water, there will not be enough oxygen for any aquatic life to live. So what we have here is some data, and again, I'm sorry the picture got a little bit cut off over here, but I've just kind of fixed it up for us. What we have over here is some information about the solubility of gases at 20 degrees Celsius. So that's kind of a cold room temperature. And what we see is that all of these gases are at least a little bit soluble. You can get a portion of a gram in 100 grams of water. And to me, the most interesting part is not that they are soluble, all of them seem soluble, but if we look at the trend, as we go down this chart, they become more soluble. And when we also look at the molar masses, we can see that the molar masses get bigger as you go down this chart. So what this is telling us is that the higher molar mass means more electrons, and more electrons means more polarizable, which means a stronger induced dipole. And that is why oxygen gas is the most soluble out of these gases, because it has the strongest induced dipole, because it has the most electrons, and it's the most polarizable. Yep. So to sum this up, the size of the induced dipole, which is another way of saying the strength of the induced dipole, has to do with a couple different things. It has to do mainly with the polarizability. So the more molar mass, the more electrons, the more polarizable, the stronger attractions. That's really the same story as it is for dispersion forces. There's the more electrons, the more of a mismatch you can get. And it also has to do with the shape of the molecule, and we'll see some data that shows that that's true. All right, just a little bit more data to show that molar mass changes the strengths of intermolecular forces is on this chart. And what it's saying is we just have noble gases here. So what's nice about noble gases is they don't really bond with anything. So we're not talking about molecules here, we're just talking about basic atoms. And as we're going down the column in our periodic table, the atoms are getting heavier and heavier, and they're getting more electrons down here. And you can see the effect. The boiling point goes way up as you get further down in the periodic table. So as the molar mass increases, the boiling point also increases. And remember, boiling point is really a measure of how attracted the molecules are to each other. The more attracted they are, the more they're going to want to stay a liquid, and the higher the boiling point is going to be. So stronger intermolecular forces means higher boiling points. Okay, let's also look at the kind of shape and how molar mass doesn't just apply to noble gases or just to atoms, but it also applies to molecules. If we look at this graph here, we have boiling point on one side and molar mass on the other. And what all these molecules have in common is they are just carbon chains. It's just that every time we go up the chart, we add another carbon and a couple hydrogens onto the chain. And what we can see is that the smallest one has the lowest boiling point, and the biggest one has the highest boiling point. So again, as molar mass goes up, boiling point goes up because the intermolecular forces are stronger. So this is what happens when the molecules all have the same relative shape, like all long carbon strings. But what happens when the molecules have different shapes? Here we have two molecules that both have the same chemical formula. They both are C5H12, but they have different configurations. This one is a carbon chain. Like this, where all the hydrogens are around the outside. And this one is a carbon chain, or a carbon kind of star, like this, where the hydrogens are all around the outside like this. Now these types of molecules get fancy names. This one's called N-pentane. That means that the carbons are in a chain. And neopentane means it's kind of in a star shape. And that's an organic naming system, so if you take organic chemistry, you'll learn how to name things in that way. All right, so looking at the data, they both have exactly the same molar mass because they have exactly the same chemical formula. But what's really different about them is that the boiling point of the N-pentane is quite a bit larger than the boiling point of the neopentane. So the long carbon chain is harder to separate from other molecules like it than the neopentane that has more of a star shape. So the higher boiling point has stronger intermolecular forces, and the lower boiling point has weaker intermolecular forces. But how can that be if they both have exactly the same molar mass and exactly the same chemical formula? And the answer is that the neopentane, with its long carbon chain, has a lot of surface area. And that means that when it's around molecules like itself, it has a larger surface area to interact with them, and a higher surface area means more attractions. The lower surface area means less attractions, just less space to attract other molecules. Now, some other words that are associated with these molecules, these are called branched chain, the ones that look more like a star, and these are called straight chain. And when we look at them compared to each other, this is a graph of boiling point versus molar mass, and these are the straight chain. The isoalkanes are the branched chain. So what this graph is telling us is that it doesn't really matter what the molar mass is. The relationship between these two here, so the red and the blue, is that the red one, the straight chain, is always going to have a higher boiling point than the branched chain. And that's true for all carbon-based molecules if they have the same chemical formula, but one has a straight chain and the other one has a branched chain. The straight chain has higher surface area and it's always going to have the higher boiling point. So these intermolecular forces can be greatly influenced by the molecule shape and by the molecule's molar mass. Now we've talked about dipole-dipole, and we've talked about dispersion forces, and we've spent quite a bit of time talking about how even though all molecules and atoms can do dispersion forces or have dispersion forces, there's a relative range of strengths of dispersion forces. There can be quite weak ones, and there can be quite strong ones that approach a dipole-dipole force. The ones that are weakest are the low molar mass and low surface area molecules. The ones that have the strongest dispersion forces are the high molar mass and high surface area molecules. And now I want to go on to hydrogen bonding and talk about how it's different than the others. Now, I wish somebody would have asked me when they named hydrogen bonding, because the word hydrogen bonding really implies that there's some kind of bond going on. And we began this video talking about how intermolecular forces, like hydrogen bonding, are not actual bonds. They're much weaker than real bonds. But for some reason, it got the name hydrogen bonding. That does not mean that it's an actual bond. Hydrogen bonding is a very special situation in which you have an attraction between an unshared electron pair on an electronegative oxygen, nitrogen, or fluorine. So that is a very small amount of molecules that have that kind of situation. It has to have an oxygen, nitrogen, or fluorine, and it has to have an unshared electron pair on that atom. And then the molecule also has to have a positive hydrogen bonded to that oxygen, nitrogen, or fluorine. Now that might seem like extremely rigid type requirements for hydrogen bonding, but we have some molecules that we've seen a lot that meet these requirements. And the big one is water. So water has unshared electron pairs on an electronegative oxygen. So those are its unshared electron pairs. Those are its lone pairs. And it also has a positively polarized hydrogen bonded to that electronegative oxygen. So it has these hydrogens on this side. Now, if you have two water molecules, the attraction between them has to do with the fact that this is a very electron-rich side, this is the electron-poor side, electron-poor side, electron-rich side. And there's this huge attraction between the partial positive charge and the partial negative charge between the two different molecules. But that right there, this attraction between the positive and the negative, just seems like a dipole-dipole interaction. It's just two polar molecules being attracted to each other, the positive side of one attracted to the negative side of the other. Now I've drawn my molecules a little bit better here and a little bit clearer. And I want to talk about how this is more special than just a dipole-dipole interaction. And I'm not saying that this attraction isn't true, but I'm saying that it's not the only thing that's going on. What I want us to focus in on is the relationship between the oxygen and the hydrogen in each molecule. We know that oxygens are much more electronegative because they're closer to fluorine in the periodic table. So when they have bonding electrons between them and another atom, they pull those electrons towards themselves. So this oxygen is pulling the electrons towards itself. And what that does to the hydrogen is it makes it even more positive. Not only does it have no lone pairs of electrons to itself, but even its shared electrons are being pulled away from it. So these are just not partially positive hydrogens, they are very positive hydrogens. And because the oxygen is pulling the electrons towards itself, it becomes much more negative. So this isn't just a partial positive charge and a partial negative charge being attracted to each other. I kind of think about it as a supercharged positive charge and a supercharged negative charge being attracted to each other. And that's what makes hydrogen bonding so special, and that's why hydrogen bonding is more strong than dispersion forces or dipole-dipole forces. It's kind of like a special version of dipole-dipole that's stronger. And that's why we find hydrogen bonding so far down on the list. It's stronger than dipole-dipole and dispersion. And it's strong, but its requirements for its molecules are really stringent. the molecules have to have a hydrogen bonded to a fluorine, oxygen, or nitrogen. So this really limits the number of molecules that can have hydrogen bonding as an intermolecular force. Now, I know not many molecules can do hydrogen bonding. Water can do it, and that's a really common molecule to us, so it's a good example. There's another one that we've seen a lot of, NH3, that's ammonia. We've seen a lot of ammonia. We've drawn the Lewis dot structure for it many times. And when you look at its Lewis dot structure, it has a negative side and it has a positive side. It's a polar molecule. And it has a hydrogen that's bonded to a nitrogen with a lone pair on it. So it also meets the requirements for hydrogen bonding. And that means that the nitrogen from one ammonia is going to be attracted to the hydrogen from a different ammonia. And that's what we call a hydrogen bond, the attraction between those. And hydrogen bonding is really special in the way that it gives water some kind of crazy properties that other molecules don't have. For example, hydrogen bonding is the reason why we have things like capillary action, we have the surface tension of water being so high, and a big one that's important to us as humans that need space on land to live, why ice floats. Okay? It's really important to us that ice stays on top of the water and not under the water. If it went under the water, our sea levels would rise and we would have less space to live on land. Now, the reason why ice floats is because it's less dense than water. And that's because hydrogen bonds allow the molecules that are in the liquid phase to get a little bit closer to each other than non-hydrogen bonding liquids do. And if we're comparing that to the solid, when water is in its solid form, in its crystalline form that we call ice, its orientation is very rigid. The molecules have to line themselves up, hydrogens on one molecule to the oxygen on the other, the way that their attractions, the hydrogen bonding would kind of attract each other, and they hold themselves in space because that attraction is really strong. But when we look at the liquid phase, the hydrogen bonding and the little bit more kinetic energy that those molecules have allow the molecules to get closer to each other than they do in the solid form. So the most dense form of water is actually the liquid state at about 4 degrees, not the solid state at 0 or below. So hydrogen bonding gives some of our molecules some really interesting properties. So now we've talked about hydrogen bonding, we've talked about dipole-dipole, and we talked about dispersion. And one thing that I want to point out for these is that we're talking about these molecules like they can only do one intermolecular force, and that just isn't true. For example, anything that can do hydrogen bonding is also a polar molecule, and it's a molecular atom, so it can do dispersion forces. So if it can do hydrogen bonding, it can do all of these. So all of them together. It's just we talk about the hydrogen bonding the most because if the molecule can do hydrogen bonding is the strongest out of these three, and hydrogen bonding will be the most important to that molecule. It's not that it doesn't also have dipole-dipole forces or dispersion forces, it's just the hydrogen bonding is the strongest, so that tends to be the one that we talk about the most, the strongest intermolecular force that a molecule can do. And the last one that we have to talk about are ion dipole forces, and I'm actually just going to use this slide to do that. Ion dipole means that you have an ion, so something that is positive or negative. An example would be a sodium or a chloride, and it is mixed with a polar molecule, so that's the dipole portion. So the combination that can do this are mixtures of ionic compounds and polar compounds. Kind of our poster child for this would be mixing sodium chloride and water together. Now what happens when you mix an ion with a polar molecule is that the ion always has a charge on it, and that charge is attracted to the part of the molecule that has the opposite charge. So on a water molecule, the oxygen side is the negative side, and that's what we see kind of showing on each one of these water molecules here. And this positive ion here is attracted to every one of these partial negative charges on the water. So it's attracted in every direction. It's attracted to every water molecule. Now the same thing would happen if we had a negative charge, something like a chloride. So if we have a negative charge, what would happen is that the water molecules would orient themselves so that their positive sides were attracted. Like this. So this is the positive side of water, this is the positive side of water, and our chlorine, or chloride ion, would be attracted to every positive hydrogen on the outside. Now because there's so many of these interactions going on, ion dipole forces are the strongest out of our intermolecular forces. So they are the strongest. Dispersion forces are the weakest, and dipole-dipole is getting stronger than that, then hydrogen bonding stronger than that, and then we finally get to ion dipole. Now ion dipole is the strongest, which explains why so many ionic compounds are soluble in polar compounds. They are so attracted to polar compounds, and so that they really easily dissolve within them. Now to practice what we've learned in this video, we'll do some practice problems that go something like, here's a molecule, what is the strongest intermolecular force that it can have? Or another problem would be, here's two different molecules, which one has the stronger intermolecular force? Now to make those choices, you have to know what kind of compounds can do each intermolecular force. And then you go down the list, and we know that all molecules can do dispersion. Only polar molecules can do dipole-dipole. Polar molecules that have a very specific formula can do hydrogen bonding. And ion dipole means you need to have an ionic compound and a polar compound. Now if you're having a hard time deciding what type of intermolecular force your molecule will have, this is kind of a flow chart to help you out with that. So the first question that you would ask is if ions are involved. If they are, it could be dipole-dipole forces. But if it's not, you're limited to dispersion, dipole, or hydrogen bonding. And London forces are the same thing as dispersion. So if you're having a hard time deciding what type of intermolecular forces a molecule can do, you can practice using this flowchart. In this video, we talked about the types of intermolecular forces. Which are dispersion, sometimes called London dispersion, dipole-dipole, hydrogen bonding, and ion dipole. We talked about the strengths and how you can use things like polarizability, molar mass, and shape to decide how strong your intermolecular force will be. Now, if you'd like some practice answering some questions about intermolecular forces, in your course pack, page 65 is a worksheet called Intermolecular Forces 2. And that would be a good way to practice some of the concepts that we've talked about.